So let me start showing you some things. Oh yeah, so this is pretty much what I already said. It's difficult to show dynamic out animations in PDF file, so we're just going to do it on my computer here. And let's get into it. So the first thing I'm going to show you, I'm going to start on the next slide. I downloaded from the Hipparcos database, the position, proper motion, radial velocity, magnitude, and color index of all stars brighter than magnitude 10. Oh, and by the way, I meant to write on this slide how many stars there are, and I forgot to do that. I think the answer is about 10,000, if I remember correctly. Anyway, I was hoping to use Gaia data because Gaia is the new thing. But the interesting.
Would you share your screen?
Oh, share screen. Sorry. Zoom. Share. And now I probably have to go out of full screen mode. Now we go escape out of here. Picking up the audio. That's better. Can you see it? Yep. And you can see it?
Yep.
Okay. All right, there we go. Okay. Yeah, so I wanted to use Gaia data because Gaia is the more modern and higher accuracy stellar data. And I downloaded that set of Gaia data and discovered the bright stars are not in the data. I mean, I think the bright stars are there, but if it doesn't have all those other things, then when I did the download, it didn't download pretty much any of the stars prior to about magnitude 5 because they were too bright for it to measure things like its proper motion because the pixels were oversaturated. Excuse me. So I used the Hipparcos data, and then I can show things and go to the next slide. This is just a screenshot, but when I click on it, we're going to actually be able to play with this web page. And here it is. I'm just going to make this bigger so it looks better. All right, so this is something I made, and oh, we're way in the future. Let's go back to now. Let's go back to resume. See Barnard star? Zooming out up there. And by the way, I put a comment here at the bottom. Of course, we scroll down. Barnard star is shown as magnitude 1, when in reality it's magnitude 9.5. So I made that one bright because that's the exciting one to see. But everything else is drawn relatively accurately. And this goes for 100,000 years. We're 54,000 years in the future now. And we can see Vega's moving. Altair is moving. All these things are moving, but not very fast. Look at that one's moving. And so all the stars move over time, which is kind of what inspired me to make this web page so that we can play with it. And so I can play with it. Here we go. 100,000 years ago, 100,000 years in the future, this is how things will move over a course of 200,000 years. And for those of you who are into physics and mathematics, you might be wondering, how did I do this, dynamics integration of the gravitational pull of things? And the answer is, I didn't do any of that. I just took its position and velocity, and I'm just plotting it as it's going in that direction at that speed in a constant way. And that's okay over the course of 100,000 years. If this were 100 million years, that would be a bad approximation because our stars go circle around our Milky Way galaxy about once every roughly 100 million years. And so at that scale, just making things go in a straight line is no good. But over 100,000 years, these stars pretty much are just going in this straight line pattern that I'm showing here. And so we can turn off the constellations if you like. We can turn off the labels. We can play with it to see how all these things are moving. And I also made, oh, I can't see it because of my, I'm going to move this down here, if you don't mind. Oh, not down there. How do I put it over here on this side? Okay, because now I can select other perspectives. This is how things look. We look north. Okay, let me put in some information here. So well, there's Polaris, the North Star, and things are moving. It starts at 100,000 years ago. Let's set it to now. This is how things are now. And if I hit resume, we can start moving again. And if I yank on this, we can make things move. Oh, Polaris hardly moves at all in 200,000 years, but all the other stuff moves a lot. So this was fun. Look at that Alpha Centauri, which is nowhere near the North Pole. Oh, 100,000 years from now, we'll be not pretty far away. Isn't that fun to watch? And, you know, all these things are moving. We all know that, but it's fun to see them, how they move. Oh, there's the Big Dipper. Big Dipper looks more like that right now, but 100,000 years from now, it'll look kind of weird. The handle will be all messed up. The shape of the pole will be weird. Is that fast track? Oh, the spatula. Yeah. So I had fun making this. This was all inspired by Barnard Star, which I talked about at great length before, but I thought it would be fun to make this kind of bigger perspective on things. Okay, let's go back to the slide. All right, so that's all I have, I think, to say about that one. All right, so stellar dynamics closer to home. I'm going to show you a link to a web page that has lots of links on that web page, showing things, not all of them are solar system, but stellar things close to our solar system. Some of them are our solar system. And I'm going to illustrate just some specific things. How many people here know what the Lagrange points are? Anybody? Okay, maybe about half of you. Okay, so I'm going to illustrate that and how stardust changes over time and some co-orbital asteroids and maybe some horseshoe orbits and blah, blah, blah. So here's a screenshot of the web page. I'm not going to show you all the things on this web page, partly because some of them will come up later, but I am going to show you stardust here, this one. I am thinking I'll show you circumbinary disk, and I think I'll show you Lagrange L1 to L5, and maybe I'll show Earth orbital, but I'm not sure how interesting that one is. So anyway, let's start. So let's open up Google Chrome. Here's the web page. This one's kind of fun to play with. And then hit pause. So what this has, which you can hardly see, you see a little dot in the middle? That's the sun. And there's a little dot over here, which you probably can't quite see, which is what we call Jupiter. And then everything else is mass zero, even though I'm drawing it as if they're kind of biggish things, just stellar dust. And I start this all off. Let's see if I can remember how to do this. Oh, let me set the time interval to go 0 and hit restart. Okay, now it does nothing. And turn off the trails. Oh, wait a minute. Oh, hit play. Oh, yes, that's not the trails. That's just all the dust. Okay, so it's hard to see anything here because all we're seeing is dust. But right over here is Jupiter, but you can't really see it. It's just looks like one of the dust particles. But now if I make this back to a small time interval here and hit the unpause it, maybe I have to hit start again. There we go. Jupiter messes things up. The things that started out close to Jupiter, oops, come on. There's Jupiter right there. That's Jupiter. That's the sun, and everything else you see is dust. And if we let this keep playing, and I can speed it up by hitting the warp to maybe 50, or how about 500? Wow. Okay, now it's going a lot faster, and the time is 300, whatever units that is, years or whatever I used. I think I used years. If we let that go for a long time, if I hit pause, there's Jupiter, there's the sun, and things seem to be kind of happy over here and kind of happy over here. Things close to Jupiter are completely knocked away, and things over here, there's still stuff over here, but it's not as nice as it is over here. And let's see, is there other thing here? Frame rotation. Oh, and I wrote in my notes up here, what frame rotation rate do I pick to, uh, I wrote it here somewhere. Does anybody see it? Do, do, do. It's 0.518. Is that right?
Yep.
Yeah, 0.518. So if I change the frame rotation to 0.518, this is counter-rotating what we see then, so that it doesn't look, oh, did you do it? Oh, maybe because this number is way too big. Oh, it didn't do it? Oh, there we go. So now we're counter-rotating our view so that Jupiter doesn't look like it's moving. It looks like it's just sitting there. And all the things we're seeing moving are the dust because it's being perturbed by the gravity of the sun and Jupiter. And again, if I go into a high speed mode here, this should be interesting. Let's
So,
go higher.
Bob, is there any significance to the colors?
No, just random, make it pretty.
Okay.
Random coloring.
so it seems like there's a stream going in opposite directions. The one on the outside is moving counterclockwise, and the one on the
Yes,
inside is moving clockwise.
yes, and that's horseshoe orbits. And we're going to talk about that. Yes, very good point. And if we let this go for billions of years, we're only a couple thousand years, I think most of this will just settle around here, which is L4, and the other part will just settle around here, which is L5, and it'll just be very close in there, and all this other stuff will just kind of be concentrated in those places. But I've never let this thing run for a million years. But if we scroll down here, I did let it go for 50,000 years, and then took a screenshot, and there's how it looks after 50,000 years. And you can see there's quite a bit of stuff, but there's more stuff sort of right here, and there's more stuff right here, and those are L4 and L5. And L4, by the way, by definition, is the dot that you make to make an equilateral triangle. So L4 is about right there. And we can talk about, well, I didn't refresh my memory. I used to know how to derive the mathematics to prove that L4 and L5 are stable orbits, but I think I don't think I could do it today. Not sure if anybody wants to see the math anyway. Yeah, so this is fun to see. Let's go back here. What was next? Okay, L3, the three body, Lagrange three body. Should we show that one? There we go. And that's stable. This is a star, a planet, and a tiny body here. And if I speed it up, things get interesting. Let's do counter rotation. Now we're counter rotating it to keep the sun in the center and Jupiter. If this is Jupiter, did I say it's Jupiter? It doesn't really matter what planet it is. We'll call it Jupiter. Keep this stationary. And then this over time, excuse me, let's speed it up another factor of 10. 200. Now, oh, that's interesting. Jupiter is also getting motion. That is interesting. I don't know why that's happening. Yeah, that's a good point, because I did put a little bit of eccentricity to make this be an accurate representation of Jupiter's orbit around the sun. If I'd done a perfect circular orbit, I think we wouldn't be seeing that. You're exactly right. But this is nice and stable. This is not being kicked around at all. We've gone almost 1,000 years. All right, let's go back. What other things to show you? Well, this is a favorite one of my Lagrange points. Boom. Those are L1 and L2. Those are periodic orbits, but they're unstable, and they go unstable quickly, as we just saw. And so that's L1, L2, this is L3, this is L4, this is L5. If we wait long enough, this one also will go unstable. I think I have to speed it up to do that. So let's make this be a 1 here. Okay, now it just went unstable. But L4 and L5 are still stable. And they're wiggling a little bit because of the of a small amount of eccentricity, I think is why they're wiggling. Although this doesn't look like it's going in and out, but I'm not sure. Yeah, anyway, it's fun to play with these things. And the sun and Jupiter, we do have what do they call those asteroids out there? The Jovian asteroids?
Trojans.
Trojans, thank you. I blank on words as I get older. The Trojan asteroids are out here and out here in the L4 and L5 area. And so this kind of is explaining a little bit about why that is. Okay, this is something I did with a student at Princeton recently, a couple of years ago. This is a binary star system, so this is not our solar system. This is two stars and then a massless planet. But I don't want to just do one massless planet because that would be boring to watch. This is a couple hundred, I can't remember the number. I think when I click on it, it'll tell us massless planets. And I'm showing them all because they're not touching, they're massless. They're not interacting with each other. And so I can have one web page that shows hundreds of these things. What is 180 planets? And so here's how these 180 planets are reacting to that binary star in the center. So they all started out with circular orbits, which were the velocities were correctly selected to match the mass of those two planets in the center to give them nice circular orbits. But because there's two things in the center, not one star in the center, that binary star system perturbs the circular orbits of these planets, these massless planets that are going around. And over here, I'm plotting the eccentricity of each planet as we go out. If I reset this and hit pause, so you can see initially the planets were just evenly spaced. Oh, and this thing over here is called Earth. I threw that one in there just to sort of give you a full perspective. And the total mass of these two stars is the mass of our sun. So this is kind of like the sun and the Earth. And the Earth is, if our sun was a binary star, we're far enough away that it wouldn't be a dramatic impact on us, but it is a dramatic impact on planets that are a lot closer. And if I hit the resume, you'll see that these ones that are really close are the ones that go berserk quickly. Oh, by the way, here I'm plotting the eccentricity, and right now the eccentricity of these really close ones is kind of pretty big-ish, 0.4 or almost 0.5 for the closest one. But we'll see that better when I restart this, and the eccentricities here, when these close ones get kicked out, the eccentricity goes to infinity or whatever. So let's watch this. So see, these things are getting kicked out quite a bit further, and that's eccentricity is being listed higher up. And I put these as just plots to give you a sense of things. So 6, 7, 8. So things fully up. This is the binary star system has a period, and so if it's going half the speed, it's 2 years binary period, 3 years binary period, and so on and so forth. So the time scale here is relative to the orbital period of the binary stars here, and so you can see the close-in ones have really gotten all messed up, and their eccentricity is going off weird. But this is really fun to watch on a longer time scale. Just watch this for. Look at that guy just got shot off. Another one just got shot off. And now I'm going to speed it up. Change this to. Let's speed up just a little bit to start with. Okay. And you can kind of see that the ones that were within some threshold, they've all been kicked out. And the ones that are outside this threshold are pretty much happy. And that's the interesting thing. Oh, I put 32 here, not 2. What an idiot. I meant to put a 2 there to make it go faster.
So this proves that gravitation is not always attractive.
It's distractive. And here's the reason I'm totally fascinated by this. The planet whose distance gives it an orbital period that's 3 times the orbital period of the binary system gets a high eccentricity, but the planets right next to it are happy. That's so interesting. I'm going to make this go even faster so you can see that bump up even more. Look at that. That one planet got sort of kicked out of here, where all the other ones right next to it, it's pretty happy. And I don't know the mathematics behind this, but this is a known thing. It's not a discovery of me. But I find it very interesting that this orbital resonance of a factor of 3 kicks this one out. But you think, oh, if resonance 3 kicks something out, maybe resonance 4 kicks something out. Oh, you do see a little pattern here. That resonance 4 is actually a little bit better at 4. Terrible at 3, better at 4. And maybe if we ran this a million years, we might see little blips at 5, 6, and 7 also. But I don't think I've ever run it that long to see anything more than this little blip down here and this big blip up here. And the fact that inside a certain range, everything is unstable. And in fact, in my notes up here, which are a little bit hard to read, I think I do mention where it's known that things become unstable. I can't see the whole page. Why can't I see my whole page? Oh, almost the whole page. Okay. Do I mention any number? It's too hard to read all these things. I don't think I mentioned where this thing is known to go unstable. But this threshold right here, which is at about 2.7, it's known that inside 2.7 things go unstable. And by the way, we can play with these mass ratios and all kinds of stuff. I can change this to 5, and because they were 4 and 6, changes to 5 and 5, another equal mass. And all of them have a very similar kind of pattern. So now the two binary stars, now you can see that they're equal mass because they're both going in exactly the same circle. When they're a little bit unequal, it was not exactly the same radius. One was a little bit closer, one was a little bit further from the center. And we can play with all kinds of things here. I don't know if you want to do all this. We can put the closest one further in. It'll make it blow up even faster. So yeah, look at that. One green one kind of looks like got into a stable orbit around there. Don't know what that is. Well, we'll see things like that in slides that I'm going to show you next. Okay, so we're done with this. That's the circumbinaries, horseshoe orbits. So I show you horseshoe orbits. This is kind of toggle counter rotation. And this is the yellow planet is, why do I call it yellow? I didn't make it yellow, it's blue. Is Saturn. And this, oh, the coloring here is all wrong. Oh.
So it says the cyan moon is Janus.
Yeah.
I think the central object is supposed to be Saturn.
No, that's supposed to be the sun. I think that's a typo. Wait. Oh, no. Oh, sorry. This is This is Cyan and Janus. Sorry, this is Janus and Epimetheus. Sorry, I didn't read my own notes here. This is Saturn. The yellow thing in the center is a planet, not the sun. And this is 2 moons of Saturn, Janus and Epimetheus, which are known to be in horseshoe orbits. See, I wrote my notes so small I can't refresh my memory quickly enough. So these are 2 moons of Saturn, which are known to be at almost the same orbital radius, and therefore they have this pattern, which is interesting. And we toggle the counter rotation, it holds Janus fixed, and we watch Epimetheus moving around. And if I speed things up, maybe make this warp 300, because that speeded up a lot. You see that this is the horseshoe orbit. Watch. This will come around. It's going faster, but it's not going to pass. Nope. It switches and goes around the other way, which is what you were mentioning before when we were seeing those dust things doing a similar kind of thing. And that's a horseshoe orbit. And that little jiggliness is because there is a little bit of eccentricity in these things. So I used accurate data rather than just sort of fun math data. If I did a fun version, mathly fun version, this would just be fixed, and this would just come in, go around. When it's closer to the planet, it's going faster. But rather than passing the other moon, that other moon pulls it up because it's pulling out a little bit, and then it goes into an orbit that's a bit further out and slower. So that's what happens is it comes faster, and then when it gets close to the planet kicks it up a little bit, and then it ends up going slower, going around to the other side, and then it gets a boost, it goes in. And so this is called a horseshoe orbit because isn't that what a horseshoe looks like? Kind of almost a circle, but with a piece of it missing. So that's the famous horseshoe orbit. All right. So most of these other things, I'm going to show you stuff later. Oh, but I could show you this one. I think was kind of fun to look at. But this one takes forever to load. And I'm putting a whole bunch of stardust in here. And we're seeing with how that stardust sort of clusters. And so that's the sun, that's Jupiter, this is Saturn. But since I'm showing multiple versions, and Saturn has some periodicity with respect to the times that we're using, redrawing this every 10 years, and Saturn has a period that's almost a multiple of 10 years. So we're seeing Saturn half the time up here and half the time down here. Anyway, that's Jupiter, and Jupiter's kept steady, and so that's why it's getting cleared out close in here. And there's a little bit of the L4 area and a little bit of the L5 area filling in, and it's fun to see how this whole thing clears out. The stuff between Jupiter and Mars kind of is getting cleared out a bit. And these are things we astronomers all know about. All right, go back. Okay, let's go back to the slides. I think that's all I wanted to show you on this page. And we could come back to more of that later. All right, so now we'll get into more fun things that I played with. I have a whole bunch of solutions to the n-body problem, where on most of them, n is just either 3 or 4. And some of these solutions to the n-body problem were things that I actually quote unquote discovered or computed, whatever you want to call it. But most of the things I'm going to show you were discovered by these two astronomers, mathematicians in China, Li and Liao. I've never met them, but I've exchanged emails with them a few times over the years. And for those of you who like physics and mathematics, I can say that the periodic orbits that I'm going to show you all of them are found by searching for local minima of a function. And the function is called the action function. It's a function of the planetary orbits. So P1 is not just a number, it's the orbit of planet 1. So this is actually a function of time. I didn't put P1 of t here. But this is a function. It's not just a number. And it's not just a single thing. It's x, y, and z coordinates also. So it's the planetary position as a function of time of planet 1, 2, 3, 4, up to n. And the formula for the action functional is this integral over the period from 0 to t of 1/2 mv squared. That's the kinetic energy of planet I, and we're summing this over all the planets. This is the total kinetic energy, and this is called the total potential energy of these pairs of planets. And finding local minima of this gives you a periodic stable solution. And by the way, all the orbits I'm going to show you are periodic because they were local minima here, but not all of them are stable, only some of them are stable. And we're going to play with this for the next 20 minutes so you can kind of get a sense of which are which. So it's just a screenshot. Go click here and go to my webpage that shows these things. This is one of my favorites, which is why it's put up here. It's called the Star of David. Does it look like a Star of David?
Mm-hmm.
And one thing I like, by the way, this is not perfectly stable. It doesn't go crazy, it doesn't go berserk, but it does start to change its rotational period a little bit, maybe in another minute or so. But here's what I like to do. Toggle counter rotation. Toggle this, and now I'm holding these two right here. Those two, let's call them stars. Those two stars are co-orbiting each other. And down here, these two are in a circular co-orbiting motion with each other. So I call this a double-double. It's a binary star system and another binary star system. And these two binary star systems are so close that they're going around each other. And I think that's really interesting. And if we get rid of that, now we can see that now the periodicity's changed a little bit. And it's not perfectly stable, but we can I've let this run forever, and I don't think it ever goes completely crazy. It just kind of goes off a little bit. So that's one of my favorite ones. And so that's the first thing here. Star of David. Here's another interesting one. And I forget who discovered this, but this is the one, when this was discovered, this is the one that got me interested. This is a stable solution to the three-body problem. And it's called the figure 8. And I've always boggles me, why don't they just call it infinity? Because they never rotate this 90 degrees and make it look like an 8. Whenever you see pictures of this or animations of this on the internet, it's always shown this way oriented. And we can speed this up, and you can see that, wait a minute. Oh, delay between frames, withdrawal, DT, 0.1 goes faster. There we go. Now we're going fast. We've gone 300 whatever time units, and it's a stable thing. We can let this go for 5 or 10 minutes. It's not going to go. Question?
Is there a star somewhere in there?
These are just 3 bodies. So we can call it 3 stars, or we can call it 3 planets. It's just 3 bodies. Which should we prefer me to call it? Stars or planets?
Orbiting each other.
Huh?
They're orbiting each other.
Yeah, they're orbiting each other.
Yeah, what's your equal mass?
Equal mass. Yes, thank you for, I meant to say that. They're equal mass. And I'm going to show you similar things with unequal mass, but most of the things I'm going to show you are equal mass, just because this is kind of more of the math nerdy part of this talk. But you know, you could have 2 stars that are very similar mass, so that's not, or a tertiary system of stars, which have about the same mass. You know, they're not going to be exactly the same, so mathematically it's not going to be rigorous. But you could have a triple star system that does look like this, and that's kind of what inspired me to think this is really fun. And you could do it, maybe you can do 4 bodies, make a figure 8 with 4 bodies. Here we go. Let's watch this one a little bit. Okay, that's what we're going to see when things are really unstable. Technically speaking, that was a perfect orbit. If my calculations were done with infinite precision, that would have lasted forever. But because this is being done on a computer with 16 digits of accuracy of my computations and a DT, which is not 0, DT, this time increment when I'm updating things is not 0. Oh, and by the way, this over here is also interesting. Leapfrog is a version of the integrating technique that I've played with a lot, and it's my favorite. But there was a postdoc at Princeton at the Institute for Advanced, a pair of postdocs at the Institute for Advanced Study at Princeton named Ryan and Spiegel. I forget their first names, damn it. They came up with this other integrator, which is better. So let's see if this one lasts a little bit longer. It still goes unstable. Yeah. So it's really just the 16-bit digit. But yeah. All right. So that one's unstable. How about this one? This is just a 2-body problem. We all know this one. 2 equal masses, both in an elliptic orbit. It's just fun to see these things. I can make this go a lot faster. Oh, that's too fast. I'll just, the screenness is messed up.
And so that's still following Kepler's law, right? The equal areas.
Yeah. Yep. So that was fun to make. And this one kind of inspired some related ones I'm going to show you next. That was just the 2-body problem. What about 3? Boom, boom. And let's speed it up. Oh, I did it wrong again. Put a 1 there, a 21. if I remember correctly, this is also stable. So there you go, a stable solution to the three-body problem.
And how many years does this represent right now? How many years have they been stable?
75.
Those are big small, later.
Yes, there is, it's coplanar. In fact, I think we can look at it from this angle. So now we're looking at it edge on. Some of the ones are three-dimensional, but a lot of these are coplanar.
Was the Star of David three-dimensional?
Say again?
Was the Star of David three-dimensional?
No, that's also planar. Yeah, yeah. Most of these earlier ones are planar, but eventually we're going to get to some 3D ones. So that's the triple ellipse. What about the quad ellipse? And that's not the quad guide. Oh, you guys watching the Olympics? Sorry, he fell. Yeah, this is also stable. Isn't that interesting? And so this makes me realize we could go beyond 4. We could go 5. We could go 6. We could go 30. We could go 120. And if these were all a perfect line and all have exactly the same mass, we could make these really interesting, stable, periodic orbits with an arbitrary number of bodies. I thought it was really fun when I thought of this. I'm not actually, I did all this, by the way, 15 years ago, so I don't remember a lot of the history of things. So I'm not sure if I'm the only one who ever did this or if other people also did it. That I don't remember off the top of my head, but I did think of this myself and do it myself. Yeah, okay, here's some more fun. Okay, here's unequal masses. So this is going to be the Star of David, but one of them is going to be mass 2, the other one's going to be mass 1/2, another one's going to be mass 1.5, and mass 1. And let me speed it up because it's really pretty to speed it up. Maybe if I speed up this way, is it better? Yeah, maybe that's a better way to speed it up. And if I hit the toggle counter rotation, you can still see it's doing the same kind of thing. And is it stable? If I remember correctly, this one's stable. Yeah, this one's stable. So they don't have to be equal mass to see these kinds of things that we're talking about. Yeah, should we go on to the next one? Okay, similar thing. Mass 2, 1, 2, 1. And let's speed it up. Isn't that cool? 2 of them are further out, 2 of them are further in. And the further out ones have the same kind of orbit, but rotate a little bit with respect to each other. And the 2 that are further in are actually sharing the same orbit. Isn't that interesting? It's really fun to watch these things. Okay, now I'm going to show you some other ones that I'm pretty sure I'm the only one who discovered these. And these aren't famous because they're unstable, but they're fun to look at. Here we have a triangle created by 3 other bodies, causing its central body to go around in a triangular shape. But unfortunately, doesn't last forever. But it was fun to make that. And inspired by that, I made, okay, how about a square with 4 bodies causing that central body to go in a square shape? That was also really fun. But pretty quickly it goes unstable. Bummer. And okay, this one's a little bit more stable. This is the 2-body problem with equal mass. So the radii from the center are the same. And this one's perfectly stable. Right, keep going down a little bit more. All right. Here we go. The Brook-Hennen. I discovered this myself also. And I showed this. I made a webpage of this like 25 years ago, something like that, and shared it with a bunch of my friends. And one of my friends maybe friend isn't quite the right word. He was a professor, a young professor at Cornell when I was a graduate student at Cornell, and I took his course when I was a graduate student at Cornell. So it's not really quite right to call him, but I've known him for what, 40 years. And so we have become friends. He did come to my retirement party. And when I first said this to a bunch of my friends, and he was on my list of people, and he wrote back to me, he says, that looks just like the logo of the motorcycle called a Ducati. How many people are familiar with Ducatis? I'd never heard of him when he told me that. And I double checked it a little bit recently, and I haven't seen a logo that looks like this, but he did have a Ducati, and he claimed that this was maybe they changed the logo over the decades, whatever. On my webpage, a different place on my webpage, I do call this the Ducati solution, not the Brookhanen solution. Yeah. Oh, that's another thing. That's what I meant to do. Hit the toggle counter rotation. Here's what's happening. Think of this as a star, and think of this as two planets co-orbiting each other in a circular orbit, pretty much. And I'm going to make other versions of this, which are very similar. And by the way, 1 year of this planet, of this binary system going around this star, is also 1 year of these two things going around each other. So I like to call this 1 month equals 1 year. So equal masses, so it's not quite stars and planets, that terminology, but we can think of this one as a star, and this as a planet and a moon, let's say, and the moon goes around once per month, and this planet goes around once per year, and this is 1 month equals 1 year. And here we have the next one. I called it 2 months per year. And isn't that cool? And if I counter rotate, you can kind of see that it's still the same thing. These two are going around each other, and this one's sitting over here when I counter rotate. And this goes around twice when the time that this goes around once. And that's how come you get this beautiful pattern, which I just think is so beautiful. Isn't it beautiful? And if I recall, this one's stable. Let's go pretty much forever. You can see it's moving a slight bit left and right, but that's just the numerics. I think the actual orbit is perfectly stable. And then it goes down to the next one by this thing called 3 months per year. And again, if we counter rotate, you can see that it's the same kind of thing. It's just this binary thing's going around 3 times in 1 year. And so we get a more interesting pattern. All right, let's keep going because I got a bunch to show you, not much time left. All right, this one, if I'm recording, is unstable, but it's fun to watch. Boom. But the fact that it even does that is kind of cool, isn't it? All right, let's go
Comes
beyond
back.
5.5 star. All right, let's go quickly. Boom, 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 boom. This one's unstable. Let's go to this one. This one's also unstable, if I remember correctly. Yep. Let's go beyond that.
You have a temporal, what is that?
I don't. Maybe I should do that. Unstable. Let me try to get to fun things. This one's very unstable. It's kind of boring to watch. Boom. I've already shown you this one. This one just precesses. Who cares? I've already shown you this one. Let's go to this one. This again, me trying to make cool things. How about a plate sitting on a saucer? Isn't that amazing that you can have something that looks like that? But it's not stable. But it is real. And here's 4 stars with the 1 month, 1 year thing. And as I recall, it was unstable. There we go. Excuse me. And here's 1 month, 1 year again with 4 bodies, not 3. So this is like a double-double. and it's going to go unstable. There we go. And oh, and this one was fun to make because it's a hexagon, but it's very unstable. But it's real. Look at that. For a little while, it looks pretty good. Well, I'm going to have to wait till it goes unstable. There it goes. And okay, this one's nice and stable. And is that one more that I want to show you? Oh, this one was discovered by a student of mine about 4 or 5 years ago. Doing this, using that minimum, finding the local minimum of that function that I showed you. And she really liked this. And so do I, but it also goes unstable if we wait long enough. But it's pretty close to being stable. It takes quite a while to go unstable. All right. Let me just pause it so I don't have to sit here wasting computer on it. Let's go back to the slides because I think I've done everything on that page. And here's the last page. And what time am I supposed to end? 5 minutes? Okay. I think I can do most of this in 5 minutes. These are the whole bunch of them that were discovered by the two people I mentioned before, Li and Liao. And they discovered a couple thousand. And I put in here, I don't know, a couple hundred. We're not going to go through all these. But on the webpage, I hope it links to some of my favorite ones. This is one of my favorite ones. Let's go here. And because this is three-dimensional, you can look at this in stereoscopic view and see it in 3D, but most people can't do that. Yeah, cross your eyes. Or go splay looking, left eye on the left image and right on the right image. Either way, it will work just fine. How many people can do that? I'm guessing maybe just me and one other person? Okay, 2 other people? Yeah. So without glasses and getting close to it, most people can't do it, but I can, and I love doing this. So I'm looking at it, I'm seeing it in 3D. It's got some beautiful structure, but because most people can't do it, I did make this version. We're just looking at a 2D, and by the way, we can play around with it. And this is stable periodic 3D orbit of 3 bodies. And Li and Liao discovered a whole bunch of these things. And this is not just random. It goes back and repeats the same path. So even though we have quite a few different things that look like orbits, it's not an infinite number if you keep going, and you keep going back to the same place. Isn't that interesting? Should I show you some other ones? I don't know which ones are the best to show. Maybe I'll show some of the boring ones. And again, we'll go 2D. And by the way, this is 3D, even though it's only 3 bodies. And it's a very interesting pattern. And if I remember correctly, this one's stable. In fact, all these are stable, if I remember correctly. By the way, yes, all these are stable. When I was making all these web pages, I discovered one of theirs that's unstable. And I sent them an email and they weren't happy. Because they claim it's stable, but I've implemented hundreds of theirs, and only one of them goes weird. And I don't remember which one, and I think I probably took the one out that goes weird. Oh, wait, no, unstable. I put the word unstable right here. This one, let's go in 2D mode. And it is a 3D thing, or so, no, it's 2D. And this one's actually unstable if we let it go for a little while. Should I speed it up? The DT to be, oh, put the 30 milliseconds to 3 milliseconds. Go faster. Yeah, it goes berserk after not too long. That's the only one of all of them that they made that goes berserk. So, yeah, hit pause on it so we don't waste my computer. And maybe I'll just show you one more. Which one do you want to see? This one here looks weird.
Do that.
Let's speed it up so it fills in quicker. Yeah. So the geometry doesn't look as similar as the other ones did to each other. although kind of in some sense, it's a similar structure. And they discovered these by sort of putting that into that optimization problem, those P's that kind of had this general pattern, but you had to find exactly the right coefficients to get those P's to actually be stable periodic orbits. But there you go. It's a three-body problem, and it follows this pattern forever. All right, I think I'm done.
Questions?
Any questions? Should I go up to front?
Yes.
I might not have any answers.
Meteor will move on orbit at the time.
Louder.
So like, the average, there's a little, the sun, it's more like maybe the moon, the actual center of the system.
Yeah, the center of mass.
Right. Does it have the notion of the center of
Center of mass is a thing. And, we want the center of mass not to move. So that's part of the structure. Yeah, yeah. So, yeah, so that's basically the whole design. Yeah. Yeah. The other question, yeah.
Some of the stable, multiple body, problem ones seem to show the bodies breaking each other. If that's happening, is it stable?
They're not really striking, they're just getting close. So these are infinitely small dots. So we're not letting them hit. So I'm just making the body big enough so they can look nice in the image together.
Okay.
They're masses. Oh, not masses. They have masses. Right. Oh, you're doing it. Specific. But the scale of things. So much money. I do have some other stuff I didn't show you. Oh, I'll show you. Fine. Disk accretion.
Your website.
These are all my websites. So I put it in, yes, you can see all these things. In fact, I put this in local host mode because I wasn't sure that I would be on the internet, but I am on the internet. So let me go out of the local host mode and go to a regular page. Where's my regular pages? I have to get rid of this. Okay, this thing here. There we go. This is a regular web page of things. And if I go to my home page, boom, boom. That's my home page. And these two links here, that takes us to that one that we were looking at. And this takes us to this last one we were looking at with all these fun things. And down here, this is taking us to the stellar dynamics. So all the three things, I showed you basically three web pages, and all three are on my main web page. But I want to go back to here and click on disk accretion. Yeah, I showed you gravitational accretion. I didn't show you this one. This one's kind of fun to watch. But why is it so small? Come on. So here I randomly put small bodies which do have a size. And when they get close together, they hit and they become a body that's a little bit bigger. And so this is to illustrate kind of how things evolve when just originally it was just a bunch of stuff and it accretes and makes planets and moons and stars, depending on what level we're talking at. And so it's fun. Reset this to start it from scratch. There we go. You can sort of see, I give everything sort of a random motion. If none of them had any motion, they would all just go to the pericenter and collapse and become one thing. But because I'm giving them all a little bit of a motion, they don't all go together. And do I give that something I can play with? I can play with the mass. I can play with the number. I can play with the G factor. Let's put a larger number in here. Let's see if I can do 800. There's a lot more stuff there. I should put in a parameter where I
Oh,
can
wow.
play with the initial velocities.
Roll the creating.
See, a lot of it's just kind of going in because I didn't give enough initial velocity with as many things. But not all of it. There you go. Isn't that cool?
Yeah.
There you go.
Bob, I'm not sure. I thought I had read some time ago that in the early history of the solar system, Jupiter was a lot closer to the sun and then got, through gravitational interactions, got pushed out, and then its movement kind of reordered the solar system.
Yeah. Yeah.
Is that accurate? I've never been able to confirm it. I thought I heard.
These are theories, and we can't go back in history to be there. But the people who do our measuring, I think Jupiter's moving away a couple feet per year or something. And I forget these numbers. Maybe that's how fast the moon's moving around Earth. But people are measuring these changes in positions, and so it is real. But understanding the physics that what caused this a little bit of a challenge, I think. But it's not just a two-body problem. If it's a two-body problem, you wouldn't expect anything to change. You just keep doing it. But because it's more than two bodies, things affecting things. Yep. Yeah.
Thank you very much.
You're welcome.
Meeting, 14th, 11:30. Right here?
Yeah.
Right here. Did you say we had a speaker or not yet? To be confirmed, okay, but thank you.
Thank you.
Just type in your name.
Yeah, just type Vanderbei into Google, because I'm the only Vanderbei on Earth besides my mom. Yeah.
Much matter.
Is interested in astrophysics and start, what would you suggest would fade? I know you're,
That's hard to answer that question.
are there any